maybe you want to explain what a neutrino really is, because I don't think
Yes,
we've
okay.
ever actually been through this. So maybe
Oh,
that
you've
would be
never
like an
had a
interesting
neutrino.
explanation. Yeah.
No.
So the standard model of particle physics is basically what tells us what all the different types of particles are and how they interact with each other at the most fundamental level. And so there are a few different types of fundamental particles. There's 6 flavors of quarks, where most of the ordinary matter that is around us is made up of just 2 of those. There's up quarks and down quarks.
Mm-hmm. Or baryonic matter.
Yeah,
Mm-hmm.
yeah. And then we can produce the heavier quark flavors in, for example, supercolliders. And then there are leptons. And so the 3 electrically charged leptons are the electron, the muon, and the tauon. So the muon and the tau are basically heavier versions of the electron. And then each of those has a partner which has no electromagnetic charge, and that's a neutrino. So there's an electron neutrino, muon neutrino, and tau neutrino. And so the thing about these neutrinos is that they have tiny, tiny masses. We originally thought that they had 0 mass, and it was quite a surprise that they did actually have teeny masses. They, as I said, have no electromagnetic charge. They have no strong force charge, so they interact only through the weak force. And so that's why they can go straight through normal matter and usually not even leave a trace that they were there. And they are produced in nuclear reactions, for example, like what happens at the core of the sun, because it's the weak force that governs, for example, neutrons turning into protons and electrons, or protons and electrons combining to produce neutrons. And so basically, when we look at the sun and we think of it as this brilliant source of photons, actually you have to imagine that neutrinos are constantly streaming out of it too, because those same nuclear reactions that produce the light that we see produce huge fluxes of neutrinos. And so for quite a while, we had this thing called the solar neutrino problem, which was that we had some astrophysical models that predicted the number of neutrinos that should be produced in the nuclear processes in the sun. And we thought we had a basic understanding of how those nuclear processes worked. In other words, how the sun shines. And then we had some very primitive neutrino detectors here on Earth, and they were only predicting about a third. They were only detecting about a third the number of neutrinos that we thought they should be finding based on what was coming out of the sun. And it turned out this was because those detectors were only sensitive to the electron flavor of neutrinos. And neutrinos actually spontaneously oscillate between the 3 flavors as they travel. So even if they start out as electron neutrinos, because of basically the weirdness of quantum physics and uncertainty, it's a mismatch of eigenstates, technically, they have a certain probability of spontaneously turning into one of the other flavors. Even in vacuum, even while they're traveling through completely empty space.
And are they equally likely to be in each one of these 3 states?
So that's actually one of the things that we've been working very hard to study over the past couple decades, is the so-called neutrino oscillation parameters. And there is a matrix that describes essentially the probability of each flavor turning into each of the other flavors. And so the answer to your question is essentially no. It's not exactly equal probabilities, and you have to consider that the mass eigenstates and the flavor eigenstates are mismatched. So each mass eigenstate, because we now know that the masses are not 0, each mass eigenstate is a different mix of flavor eigenstates and vice versa.
Okay, so it doesn't like directly depend on each other. So like it could so that's why it can be like disproportionately equal. That's why it doesn't have to be all equal probabilities, what you're saying.
What I'm saying is that the terms in the 3 by 3 matrix that describes the oscillation are different
Or
sizes.
different sizes. Okay. Okay, so okay. Okay, yeah. So okay, sorry, continue.
Yeah. And so basically, the Sudbury Neutrino Observatory was the first neutrino detector that had the technology to detect all three flavors. And so we solved the solar neutrino problem by seeing that a third of the neutrinos that we were catching were electron flavor, and approximately two-thirds were muon and tau flavored, and that if you combine all of those together, you get an observation that matches what had been predicted by the astrophysics models of what was coming out of the sun. So this was the solution to the solar neutrino problem.
And what is the fundamental difference? Like when you said it can only detect electron neutrinos, like what is the fundamental difference between like detecting an electron neutrino versus that of a tau or a muon, for example?
Right. So basically, it comes down to what is actually happening in the interactions in this giant tank. So first, picture in your mind a giant sphere that contains literally a ton of heavy water. And then you put photomultiplier tubes, which detect very small flashes of light, all around the outside of this transparent sphere. So that anytime there's a tiny flash of light inside the sphere, one of these literally thousands of photomultiplier tubes on the outside will pick it up. And in fact, several of the photomultiplier tubes will probably pick it up at the same time. And then you put this whole thing on a support structure and you bury it 6,800 feet below the surface of the Earth. And the reason we have to bury it is that otherwise cosmic rays and all kinds of other stuff happening on the surface would, make things constantly flash inside this giant transparent ball.
Hmm.
And so, yeah, we put it at the bottom of this deep, dark mine shaft where almost nothing else is happening in it. And we wait for every once in a while a neutrino to travel right through the rock and travel right through the acrylic that makes up the sphere and interact with something in the heavy water. So then the question is how exactly is that interaction working? And so it can interact with an electron in in one of the hydrogen atoms, usually, or it can interact with the nucleus. And so this basically means that if it's an electron neutrino, it can go through what we call a charged current reaction, where it interacts with the electron, because each neutrino can basically have a special interaction with the charged lepton that it's paired with. So a muon neutrino or a tau neutrino will not interact with an electron
Hmm.
through the charged current reaction that an electron neutrino interacted. Okay, but all three flavors can have what we call neutral current reactions, where it basically gives the whole thing a shove over, and so you get this tiny sort of recoil effect that you see from sort of the nucleus as a whole. And so essentially you can count the number of neutral current reactions, and you can compare to the number of charged current reactions. And then that gives you, what is the ratio of electron neutrinos to the ratio of all of the different flavors of neutrinos.